What if you could tour the life story of the cosmos in the time it takes to brew a pot of coffee? Strap in. Stephen Hawking's landmark guide to space, time, and everything between is about to unfold in your ears. 1. Cosmic Beginnings. How Humanity Learned to Measure Infinity. Imagine looking up at the night sky 2,000 years ago, convinced that Earth sat motionless at the center of a crystal sphere. That was the worldview of Aristotle and Ptolemy, the intellectual cornerstones of antiquity. Their universe was comforting, symmetrical, and, most importantly, finite. Yet even then, a seed of curiosity had been planted. Why do the heavens move the way they do? Stephen Hawking begins a brief history of time by guiding us through this ancient curiosity and the long-running quest to decipher celestial motions. Copernicus dared to suggest that Earth circled the Sun. Galileo, peering through a telescope in 1610, saw Jupiter's moons and realized that not everything orbits us. Isaac Newton completed the intellectual coup with his laws of motion and gravitation, replacing crystal spheres with invisible forces that tug on every star and planet. This first leg of Hawking's journey is more than a history lesson. It is a meditation on the power of testable ideas. Newton's equations could predict the tides, calculate eclipses, and allow an apple and the moon to follow the same mathematical rules. For almost 200 years, the Newtonian universe looked perfect, predictable, eternal, and flat, like an infinite chessboard where God set the pieces but never meddled again. Then, in the early 20th century, Albert Einstein cracked that chessboard in 2 strokes. His special theory of relativity insisted that space and time are woven together, space-time, and that nothing outruns light. A decade later, general relativity revealed that mass bends this fabric, giving gravity its elegant geometric explanation. Instead of an invisible force, gravity became the shape of space-time itself. The risky proposal matched observations of Mercury's orbit and starlight skirting the sun, propelling physics into an era where geometry decides destiny. Hawking frames these conceptual leaps as a human drama. Each new model expands our mental territory, erasing the presumed edge of existence. From geocentric cages to a four-dimensional continuum, we have learned that our intuitive senses are poor guides to cosmic truth. The first section of his book therefore sets the tone. If history teaches anything, it is that knowledge grows by overthrowing certainties. We stand today on the shoulders of rebels who dared to imagine the universe differently, and the story is only getting stranger. 2. The expanding universe, from static stars to a primordial bang. By 1929, Edwin Hubble had aimed his telescope at distant galaxies and made a discovery that rattled even Einstein. Those galaxies are fleeing from us, and the farther they are, the faster they recede. The universe is not static, it is stretching like dough leavened by cosmic yeast. Hawking pauses on this breathtaking realization because it rewrites the narrative arc of time itself. If galaxies are racing apart today, rewind the tape and they must once have been densely packed, perhaps compressed into a single fire-hot point, an initial singularity. Here, Hawking introduces the Big Bang, a theory often described but rarely unpacked with such clarity. The early universe was a seething plasma, opaque to light, governed by nuclear forces that forged the first protons and neutrons within minutes. Hundreds of thousands of years later, temperatures cooled enough for atoms to form, allowing light to stream freely and create the cosmic microwave background, an afterglow Hawking likens to the universe's baby picture. Yet a nagging puzzle remains. Why is the cosmos so uniform? Regions billions of light years apart seem to have the same temperature, even though they have never communicated at light speed. To solve this, Hawking discusses inflation, a theory from the 1980s that posits a brief, blisteringly fast expansion in the universe's first fraction of a second. Inflation would have ironed out wrinkles, stretched quantum fluctuations into the seeds of galaxies, and left subtle temperature variations that satellites such as COBE, WMAP, and Planck later confirmed. Hawking also explains dark matter and dark energy, placeholders for gravitating mass we cannot see, and a repulsive pressure that currently accelerates expansion. Together, they make up about 95% of the universe's content, relegating ordinary atoms to cosmic wallflower status. In concise prose, Hawking stresses that ignorance of composition does not negate our quantitative grasp. We can measure expansion precisely even if we still debate what fuels it. The central theme of this section is humility. Every time we pin the cosmos down, new questions squirm loose. The expanding universe solves the riddle of why the night sky is dark. Infinite static stars would blaze non-stop. But it also forces us to confront beginnings, endings, and the chilling prospect of ultimate isolation as galaxies drift beyond reach. Hawking invites listeners to feel both the thrill and the existential vertigo. We live in a universe with a birth certificate, and its future is written in the language of expansion. 3. Black holes and quantum puzzles, where physics meets paradox. If the Big Bang tells the story of the universe writ large, black holes are its punctuation marks, dense regions where gravity's pull is so intense that not even light escapes. Hawking guides us from the theory's 18th century roots, when Jean-Michel and Pierre-Simon Laplace mused about dark stars, to Carl Schwarzschild's exact solution to Einstein's equations during World War I. A black hole's boundary, the event horizon, hides whatever falls in, but Hawking makes clear that the drama heats up, literally at the edge. Classically, a black hole seems like a cosmic jail. Information goes in and never comes out, violating no known laws, but raising uneasy questions about determinism. Hawking's own seminal contribution was to apply quantum field theory to curved space-time in the 1970s. The result shocked the scientific world. Black holes are not entirely black. Quantum fluctuations near the horizon let pairs of virtual particles appear. One falls into the hole while the other escapes as Hawking radiation. Over mind-boggling timescales, a black hole can evaporate, shrinking until it potentially explodes in a final flash. This insight braids two previously incompatible frameworks, Einstein's general relativity and the probabilistic world of quantum mechanics, and sets the stage for one of modern physics' fiercest debates, the information paradox. If a black hole evaporates completely, what happens to the details of the matter that fell in? Quantum theory says information cannot be destroyed. Relativity seems indifferent. Hawking does not claim a final answer, but he frames the problem as a crucible from which a deeper theory of quantum gravity must emerge. Along the way, listeners are treated to curiosities such as time dilation. An astronaut orbiting a black hole ages slower than her twin on Earth, and gravitational redshift, which stretches light to longer wavelengths. Hawking's exposition remains vivid without reducing the phenomena to mere party tricks. Black holes, he argues, are natural laboratories where our mathematical languages clash, forcing us to clarify their grammar. What sounds like abstract theorizing has practical echoes. GPS satellites correct for relativity daily, while particle accelerators mimic cosmic conditions to look for miniature black holes. In Hawking's narrative, black holes transform from terrorizing vacuum cleaners into engines of discovery. They remind us that nature not only allows the bizarre, it often prefers it. 4. Toward a theory of everything. Strings, boundaries, and human meaning. With black holes exposing the rift between relativity and quantum mechanics, Hawking turns to the ultimate scientific grail, a unified theory that stitches all forces and particles into a coherent tapestry. He surveys candidate frameworks, supergravity, in which fermions and bosons partner through supersymmetry, and string theory, which replaces point-like particles with vibrating loops and membranes existing in up to 11 dimensions. Although experimental proof remains elusive, Hawking's tone is cautiously optimistic. He reminds us that unification once seemed fantastical when James Clerk Maxwell merged electricity and magnetism in the 19th century. History favors bold synthesis. Hawking introduces his own no boundary proposal, co authored with James Hartle, which imagines the universe as a four-dimensional surface without edges, much like Earth's 2D surface has no starting point in the east or west. In this picture, time itself could behave like a spatial dimension near the Big Bang, smoothing out the singularity and eliminating the need for a metaphysical first cause. Whether this idea survives future data, it illustrates Hawking's deeper message. Mathematics can describe realities that transcend everyday intuition. Yet a grand theory is not purely an ivory tower trophy. It could answer why the constants of nature, masses of particles, strengths of forces, take the particular values that let stars burn and life arise. It might reveal hidden symmetries or multiverses where those constants differ. Hawking does not shy away from philosophical implications. If multiple self-consistent universes are possible, our cosmic address may be a lottery ticket in a vast ensemble. That prospect can feel diminutive, but Hawking flips the script. Conscious observers, however tiny, are the universe's way of interrogating itself. In acknowledging our insignificance, we fulfill a profound role. As the book nears its close, Hawking underscores the democratic spirit of scientific inquiry. The laws of physics are universal. The equations that govern quasars also describe the neurons crafting this audiobook. By making advanced concepts legible without equations, Hawking hoped to invite more minds into the conversation, accelerating the day we decode the final chapter of Nature's Rulebook. The section ends with a gentle challenge. Whether the unified theory arrives tomorrow or in a century, each question we answer spawns new frontiers. The true legacy of A Brief History of Time is not a catalogue of facts, but a posture of relentless curiosity, a commitment to looking into dark corners, armed with reason and expecting the universe to yield its secrets.